Centripetal acceleration. Period, or capital T, is the amount of time it takes for an object to travel one full cycle around a circle. So, for example, if this was the sun and this is the Earth, as the Earth moves in orbit around the sun, you might say that the period that it takes to do so is 365 days. Or about 31 million seconds, since period is technically measured in seconds. Frequency, which is represented by the letter F, is the number of times an object cycles every second. So if the period of the Earth going around the sun is 31 million seconds, the frequency would be the portion of that path that it would travel every second, which would be 1 over 31 million. Frequency is measured in hertz, and frequency is commonly used to describe waves. So a high frequency wave has many cycles or wave crests and troughs per second, and a low frequency wave would have a lower number of wave crests and troughs per second. You might be wondering the difference between period, which is capital T, and time, which is little t. Both of them are measured in seconds, and both of them are a measure of time. But period specifically is the time period for an object moving in a circular path. And little t for time is specifically referring to generic time, or usually time of an object moving in a straight line. So they're both measured in seconds, but they're measuring technically different things. An object undergoing circular motion or moving in a circle can accelerate even if it's not speeding up or slowing down. When you imagine acceleration in your brain, you usually think of an object speeding up or slowing down, but remember that the definition of acceleration as a vector is that acceleration is a change in velocity over a change in time, and the velocity is made up of a speed and a direction. So remember that your velocity can change by changing speed or by changing direction. So an object that has a constant speed can have a changing velocity if the object's direction changes, meaning that it's accelerating. As an object moves in a circle, its velocity is going to be tangent to the circle and represented by v with a little t next to it to show that it's tangent. Here's the equation for tangential velocity. You might remember that our previous velocity equation was displacement over time, but our tangential velocity equation is going to measure distance over time, or speed over time, because remember, as it moves in the circle, it can still change velocity even if it's not speeding up or slowing down. And that as it moves in the circle, a complete circle has a displacement of 0. So as we're measuring its tangential velocity, we don't want to have to subtract it as it moves in the circle. We want to know how far it travels along the circumference of the circle, which is why we can also describe it as circumference over time. As described in its name, it is directed tangent to the circle. So as an object spins around, if the object were to be released at, say, this point, it would move off tangent to the circle. Its acceleration is pointing towards the center of the circle, but its velocity will be tangent. That makes sense, because if you were to release the object at this point, it would become an object in motion. And Newton's second law says that objects in motion will stay in motion in a straight line at the same speed unless there's an outside force. So if this is released, it'll move off in a straight line at the same speed. Over here is a video clip of a demonstration of how this works, if you would like some more clarification. Here's an example. Let's say that you're standing and you're whirling this ball around your head in a horizontal circle, like a lasso, and you want to lasso something. Let's say you want to lasso a cow. So here's you, and you're spinning this lasso around, and you release it at just this moment. Where does the cow have to be in relation to you? Does the cow have to be in position A over here to the left of you? Or can the cow be over here in position B? Or is the cow over here in position C? If you've ever tried to lasso a cow or do something similar in real life, you'd realize that the cow would have to be here in position B. And that makes sense because the lasso, as it's released, will move off in a direction that is tangent to the circle. Next up is centripetal acceleration. Centripetal meaning center seeking. The direction of which is towards the center of the circle, which makes sense that its name means center seeking. Here is the equation. Actually, that's slightly incorrect because that should be a little a instead of a capital A. So here's your equation. And you can see from this diagram, once again, that the velocity is tangent to the circle and that the acceleration is pointing towards the center of the circle. And you might ask, why is it pointing towards the center of the circle? And it all has to do with vectors. You might remember that when two vectors are being added, let's say you have a vector of 3 and a vector of 5. If you're going to add those vectors, you would add them together tip to tail with one of them touching the other one's butt, and its total resultant vector, for example, would be 8. But if these were opposing vectors, say this one was 5 and this one was 3, then the resultant vector would be this direction with a direction of 2. So if you think about it, how did you subtract these two vectors? What you did was you took one of the vectors and you flipped it on its axis. You created a mirror. So if you're taking a look down here at these two vectors, if these two vectors here, this one and this one, were going to be added, adding the vectors, just like you did up here, would involve taking them and positioning them tip to tail, which they already are, and then drawing the resultant vector from beginning to end. But if you were to subtract the vectors, then one of them, such as this one, would have to be flipped. The same way that we flipped this guy, we'd have to flip this vector along this axis like this, and it would end up in this position right here, and its resultant vector would be this, pointing towards the center of the circle. And you might ask, why do you have to subtract the vectors at all? Well, that's because acceleration is a change in velocity over a change in time. And change means final minus initial. So you have to take the two vectors and subtract them to find the change. And that's what's causing this resultant vector, or the change in velocity, which is the acceleration vector. That's what causes that to point towards the center of the circle. This is just for fun. This is showing where this equation right here comes from. And it's coming from these two similar triangles. You can see that this is a chord length as an object moves along the circle, represented by vector d, and this is the radius of the circle. So the ratio of this distance and this radius is going to be a similar triangle to the ratio of this resultant vector and its velocity vector right here. So if you set these up as a ratio and then substitute in the fact that velocity is position over time, you can work your way down to achieving this equation. So this is just showing you that this equation isn't random, that it comes from somewhere mathematically, and that this is where the equation is derived. Here's our first example. It says, short track speed skaters can cover the 500 meters of a race in 45 seconds. It's important to note that the racetrack of a speed skater looks kind of like this. It is long and it has roundy bits along the end, but it's not a circle. So this 500 meters is the distance around the entire thing, and that the radius from one end to the other, as given in the problem right here, is 11 meters. Okay, so they travel around this 500-meter track in 45 seconds. So we are looking for the magnitude of the skater's centripetal acceleration. And we know that acceleration is v squared over r. But in staring at the information we know, we have a radius, but we don't have a velocity. This becomes more confusing when you realize that there's two equations for velocity and that they don't exactly produce equal answers. So which one do you pick? You'd have to pick this one. Since this is not a circular track, you can't say that its circumference is 2 pi r because it doesn't have the radius of 11 the entire time. So you'd pick this as your velocity, which is 11.1, and you can put that into your acceleration equation to get a total centripetal acceleration of 11.2 meters per second squared. Here's our next example about a car turning at an intersection. You have a radius of 25 and an acceleration of 3.92. What is the maximum velocity that you can drive through this turn? You've seen this in driving, that every banked turn, like to get off, for example, the highway, there's like a little sign that says a speed limit of like 30. And you're like, what do you mean? Why is the speed limit 30 on the highway? Well, that's because when you have a circle with a small radius, such as an exit ramp, that you have to slow down, or else you're not going to be able to accelerate properly and keep your footing on this exit ramp. So let's calculate the velocity you'd need for a turn of radius 25. Acceleration is v squared over r, and this gives me a velocity of 9.9 meters per second, which is about 22 miles an hour. This last one is a little tricky. It starts you off with a circular saw blade with a diameter of 25 centimeters, meaning that its radius is 12.5 centimeters, and it spins at 3,600 RPMs. How much time is required for one revolution? We can use the fact that it spins at 3,600 RPMs, which is revolutions per minute, to convert that into seconds, saying that there are 60 revolutions in every 1 second. But our problem isn't looking for how many revolutions per second. What we're actually looking for is seconds per revolution, which is why our answer has to be the inverse of this, which is 1 over 60, or 0.017. Part B. How fast is one of the teeth at the edge of the blade moving? That means that we are looking for a velocity. We have to make sure that we include our radius in meters instead of centimeters. And I got 47.12. Our last step is to calculate its acceleration. And I got 17765, and with sig figs, that becomes 18,000. Smarter Every Day is one of my favorite YouTubers, and this video clip shows him arguing with one of his friends about which direction the water in this sprinkler will move. Will it shoot out this way? Will it shoot out that way? They're not sure, so they build this device to check it out. If you're looking for some supplemental exploration about this topic, this is a really cool video to watch.